Jai Hind. In today's lecture, we'll talk about one algorithm design technique, that is greedy algorithm. In this particular topic, we are going to cover the concept of greedy algorithm, what is the approach for greedy algorithm. Then we will talk about the algorithm for minimum spanning tree, which follows the approach of greedy algorithm. We'll start with minimum spanning tree introduction, and then we will cover two algorithms, Prim's and KRUSKAL'S, to draw the minimum spanning tree. So let us start with the topic. So first of all is, what is greedy algorithm approach? When we design our algorithm, our programs, and we are having number of ways to do to do the designing. For example, our divide and conquer method, dynamic programming, greedy algorithm, so many choices are there. So now the point is when to take greedy algorithm. The algorithm always makes the choice that looks best at the moment. When we are applying the greedy algorithm, what we will see, we will be greedy about the current scenario. What we mean by the greedy about the current scenario, it means at the moment, what best will be seen to us, that we will consider. So what does it mean when we are talking about that current situation? It means we are making a locally optimal choice. So what we are going to take, the optimal choice we will do, we'll choose the optimal solution in our local scenario. Okay, in the hope that this choice will lead to the globally optimal solution. So what we are assuming that if we will do the optimal choice in surroundings, then finally when I'll go to beyond this, I will move to further global area, then because this is the optimal solution, the final solution will also result in the optimal solution. Although these not yield optimal solution always, but these are providing us, the greedy approach is providing us best solution in many areas. It has been applied to many areas like activity selection problem, Huffman coding, minimum spanning tree, and shortest path. In this particular lecture, we will talk about minimum spanning tree algorithms. Before that, let us explore the greedy approach. So when you need to go for greedy approach, what are the elements for this greedy strategy? So first one is greedy choice property. A globally optimal solution can be arrived at by making a local optimal choice. So what is the point? The problem to be solved using greedy algorithm will have this type of scenario, that the optimal solution will have the local solution optimal. For example, if I have to go from one source to destination, the best path from source to destination will definitely have the best path between two intermediate cities that are lying on the best path. Optimal substructure, that is what we are talking about. Optimal solution contain optimal sub-solution to sub-problems. So these are the points, these are the greedy elements. What is the method? When we use the greedy method, we find the solution at any instance, which solution is better. So what we do in this, firstly we select. The function selects an input from the input vector and removes it. The selected input is assigned to X. So firstly, we will do the selection among local possibilities. We are talking about local optimal solution. Okay, so firstly, we will talk about the selection. We'll do select the best thing which is locally. We will have the greedy approach when we are doing the selection. After doing the selection, we'll check, is it feasible that it can be included in solution vector? So second point is feasible solution determines whether A can be included in the solution vector. Okay. Now, if it is feasible, then we add it to the solution. So combines X with the solution and update the objective function. Okay, so firstly we will do the selection from the local choices based on greedy value, greedy approach. We'll try to take the best one. Okay, for example, if I have to choose objects from a set of objects, I'm greedy in that I'll select which is having the maximum worth. Feasibility is where I have to put these after selection. Okay, for example, if I have to take some element, I have to select objects, and in objects I am having a bigger object like TV. Can I put that in a bag? So that is the feasibility. If I'm having a costly vase on in the room and I pick it up that and I put in the bag, it is feasible. But TV cannot be put in the bag. Okay, so that is the feasibility. If it is feasible, then we add to union. Okay, we'll take the example of spanning tree and then we will consider these all points. So that is our greedy approach. So the algorithm can be taken as I'm having set of inputs. A is my set of inputs. Initially, my solution is 5. Okay, so what I'll do, I will do the selection from A. My input is the set of objects. So it is, I'm taking here A. Okay, n inputs. From there, what I will select? I will select the best according to greedy approach. Now I will check, is it possible to put it in the solution? Okay, if I add it to the solution, that is union. If the union of this selected X is possible to put in the, if union of this is possible with the solution, if it is feasible, then we will put it in the solution. So selection, feasibility and union. This is our greedy approach. And finally, we will return the solution. So this is the way of designing. This is one way of designing algorithm, the greedy algorithm, greedy approach. The greedy approach will discuss with one problem, that is of spanning tree. So firstly, we should know what is a spanning tree. If I am having this graph, I am having 4 vertices A, B, C and D. So what will be the spanning tree? Spanning tree will be a subgraph of the given undirected graph that contains all the vertices. It means in the spanning tree, all the vertices A, B, C, D will be taken. So let me take all the vertices A, B, C and D. All the vertices have been taken. Okay, that contains all the vertices and is a tree. Is a tree means it is connected as well as acyclic. Okay, so when we are having four vertices, it means we need n, for n vertices to be a tree, we need n minus 1 edges. So if I consider these 3 edges and exclude this one, this I have excluded. Okay, this is a spanning tree. For a particular graph, we have minimum spanning tree. For example, if I drop this one, so what edges I will have? A to D, D to C and C to D. The standard application is to a problem like phone design, network design, traveling salesman problem in the design of electronic circuitry. Because when we are making the network design, we want to lay down the minimum wires. So what we will have, the spanning tree. All nodes will be connected. Okay, so that will be a tree. So these are different applications. Now, when we are laying a network design, so what is our main aim? We want to make it cost effective. It should be feasible. So what we'll try to do, we'll try to apply the minimum cost. Our aim is to have the minimum cost. So the cost of the minimum spanning tree is the sum of weights of all the edges in the tree. Okay, so if I consider this undirected graph and I drop these 2 edges, so what we have included here? We have included this edge and this particular edge in the spanning tree. So what will be the cost of this spanning tree? 4 plus 5 plus 2, that is 11. Okay. If I consider this particular, in this what we have dropped this edge and this edge. So what we are getting 4, 1 and 2, that is 7. So if we consider the 7 one, that is more cost effective. Okay. So that is our requirement. The minimum spanning tree is the spanning tree where the cost is minimum among all the spanning trees. Okay. And it could be also be the case that we are having more than one spanning tree. So now our problem is to find these minimum spanning tree. Let us discuss. So what is problem? We are given a connected, undirected, weighted graph. We find a spanning tree using edges that minimize the total weight. That is minimum spanning tree. Okay. The minimum spanning tree from a given spanning tree can be found using following algorithm: Prim's algorithm and KRUSKAL'S algorithm. Now let us discuss both the algorithms one by one. First one is Prim's algorithm. In Prim's algorithm, we select nodes. Okay, select any node. Any node can be taken as source node. Then what we will do, choose the minimum cost adjacent edge. Which node we have considered, from there we will take the minimum cost edge of the selected node, and we'll go on doing this until all the nodes have been explored. Okay, so we will start with the node, then we will find out the adjacent node based on the edge which is having the minimum cost, and finally we will reach to the spanning tree which is having the minimum value, minimum weight. So let us explore this algorithm, how the algorithm is done, how we select edges, how do we draw it. So this is our algorithm. We are given a graph, we are given weights, and we are given the vertex from where we have to start. So we have taken that R. So what is the first point? We need to make a queue. We need to explore all the nodes starting with the source node. So to keep track that we have explored all the nodes or not, we have made a queue. Okay, now what type of queue it is? Is it FIFO queue? No, it's priority queue. Why priority queue? Because in Prim's algorithm, we take that edge adjacent node on which the weight is minimum. Okay, so it will be a priority queue. Which node will be deleted next? Which is having the minimum value of the adjacent edge. Okay, so starting with the total queue, firstly, from where we are starting? R. So R will be assigned value 0 and all others will be assigned infinity. All the nodes will be given initial key value 0 to the source node, start node from where we are starting, and others infinity. And same, as we need to connect the nodes, so we will take care of the parent node also. So because the starting node is this, so parent node will be kept as null. Initially, we'll not take care of the connection with this. Others will be taken care, and finally we will get the connected tree, connected graph. So we have created a queue and we have assigned the key values. Now after doing this, what we will do, we will go on deleting from priority queue the elements, and we'll go on doing this until priority queue is not empty. Okay. So firstly, which element to be extracted from the priority queue, which is having the minimum key value. So let us consider that one is U. Now what we will do, we will see all the neighbors of U. Okay, for each V belonging to adjacency list of U. It means neighbors of U which are adjacent to U. If V is still present in Q, we'll take all the neighbors one by one and we'll see, is it still in Q? That is, not yet processed, and the weight of edge from U to V is less than the key value of V. There has been assigned some values to all the nodes. If this is less than that, then we will set the key value on this new lesser value, that is the weight of the edge from U to V, and parent of V will be set as U. It means the connection is from U to V. This is Prim's algorithm. This we will go on doing until the queue is empty. Okay, so now let us understand it with an example. So I have taken here a graph in which A, B, C, D, E, 5 vertices are there. Okay, let me consider A as the source. A I am considering as start node. So how many other nodes are there? 4. So A, B, C, D, E. What A will be assigned? Key value 0, because from here we are starting. Then others will be given key value as infinity. Key value is assigned as infinity. Okay. Now, what is there in Q? In Q, all the vertices will be there. What are the vertices? A, B, C, D, and E. We are having 5 vertices. So, this is our priority queue. Which will be deleted? The deleted one will be with minimum key value. Okay. So, one more thing is we have to keep track of the parent node. So, parent node of start will be null. Other parent node will keep track accordingly. Okay. So, what we have to extract the minimum key value node, that is A. So, we selected A. Okay. Now, all the neighbor nodes of A will be checked. What are the neighbor nodes of A? B, C, D, E, all. All are neighbors of A. Okay. Now we'll see from A to B. A to B, edge is 1. Already stored is infinity. What is key value of B? That is infinity. 1 is less than infinity. Yes. Reset. Okay. Value has been reset. See this. Key value of V is the weight of U to V, as well as U will become parent of V. Okay. So, what is parent of B now? A. This is the parent record we are keeping. Parent. Okay. C. Now, A to C. A to C, this is 7. 7 is less than infinity? Yes. Reset. Parent node is A. Okay. A to D. A to D is 10, which is less than infinity. Yes. Parent node will be A. Okay. A to E, 5, which is less than infinity. Yes. Okay. So, what happened? We found a lesser value edges than keys. So, in this particular iteration, all the values have been reset. Now, what is second step? What has been done? A deleted. What is second step? We'll go on doing this until the queue is empty. Okay. In queue, we are having all these values B, C, D, E. So, we'll select minimum among these, that is B. So, what is selected next? That is B. Now, we will see neighbors of B. What are neighbors of B? Neighbors of B are A and C. A is not in the queue. Okay, what is getting deleted now? B. A is not in queue. C is in queue. So, we'll check for C. Okay, so B to C edge is 3, which is less than already stored, which is 7. So, we'll reset it. Others will remain same because those are not the neighbors. These are not the neighbors of B. Okay. Now, what we will do? What is left in queues? So what has been changed? C's parent. C's parent has been changed as B. Because from B we have changed the value. Now what will be selected next? 3. So what is 3? C. So C is deleted from the queue. Now what are neighbors of C? Neighbors of C are B, which is not in Q, A, which is not in Q, D. D is in Q. Okay, from C to D, the edge is 4. And what is value for D? That is 10. So reset. E is not the neighbor. Okay, now select next value, minimum, D. So what will be deleted this time? D. D has been deleted. Okay, so now what are neighbors of D? Neighbors of D are C, A and E. C and A are already deleted from priority queue, only left is E. So what is D to E cost? That is 2. And what is stored here? That is 5. So reset. Parent node also to be reset. When we took this from C, okay, D's value has been changed when we selected C. So parent node will also be updated. Now, what is parent node of E? It has been changed. Now the parent node of E will be C. Okay, now 2 will be selected. E is deleted. What are neighbors of E? A and D, which are not in Q. Q is empty now. We'll stop here. Okay, so we have found our minimum spanning tree. What is minimum spanning tree? What is parent node of A? Null. What is parent node of B? That is A. This is the parent node of B. A means these will be connected. What is parent node of C? B. So it will be connected. What is parent node of D? That is C. C is the parent node of D. So it will be selected. Okay. Okay. What is parent node of E? E we have updated with selection after D. So parent node will be D. E's parent node will be D because E's value has been changed after D. So parent node of D, E is D. Okay, what is this cost? 1. This cost 3, 4, 2. So 1 plus 2 plus 4 plus 2. 1 plus 2, 4 plus 4, 8 plus 10. So what is minimum spanning tree here? That is 10. What is the cost? 10. And this is the structure. So this is minimum spanning tree using Prim's algorithm. Okay. So now we'll study the second one, that is KRUSKAL'S. KRUSKAL'S algorithm works for edges. Prim's algorithm we have discussed. We started with one vertex and we go on exploring all the vertices with the minimum cost adjacent edges. That was the approach. Now in KRUSKAL'S, what we do, we take the minimum weighted edges and we include that in graph. And we go on doing this until all the nodes are explored. Okay. So what we will do, we will select the minimum weighted edge. So when we are talking about the minimum weighted edge, it means we are talking about the order of first minimum, second minimum, so on. So let us discuss the algorithm. It means we need the sorted list of edges. So how KRUSKAL'S work? We'll make the tree with minimum cost edges. Now, when I'm taking the minimum cost edges, I have to take care that it will be a tree. So there should not be any cycle. So when I'm saying that there should not be any cycle, what does it mean? It means I need to take care of the cyclic form. Okay, so we will go on adding the increasing weight edges if it is not forming the cycle. So that will take care. We need to take care of the cycles. cycle should not be formed because it is a tree. The minimum spanning is a tree, it's not a graph. From graph, we are making a tree, so we need to remove all the cycles. So for that, we will understand the concept of sets. What we will do, we will use the disjoint sets when we will add edges to the tree to form the minimum spanning tree. Okay, so initially our tree will be empty and all the vertices we will keep in disjoint sets. Okay, so we will make the disjoint set of all the vertices. Now we will sort edges, the set of edges in increasing weight. We will sort edges as the increasing weight. Now we'll select edges one by one from the sorted order, and we'll see their endpoints are in disjoint sets or not. If those will be in disjoint set, then those will not form the cycle. Okay, so we'll check those that are in different sets or not. If in different set, then we will include. It means these will not form the cycle. Their parent nodes are different. That record we are keeping with help of the disjoint set. Okay, and then we will union the parent sets, because parent sets needs to be different. If those will not be different, then there is chance of cycle. So this will keep track. This is our algorithm. Initially, we will make different set. We will sort the edges in increasing order, and then we'll take edge one by one. Okay, and we'll include in tree if these are in disjoint set. So now let us understand with the help of an example. So the same example I have considered. How many vertices are there? A, B, C, D, E, 5 vertices. Okay, so what is the first point? My tree is empty initially. Okay, and what is the other point? What is the other point? I am having 5 vertices. So to avoid cycles, I'll keep all the vertices in disjoint sets. Okay, so I'm taking 5 sets. A, B, C, D, E. All the vertices are in different sets. Sets are disjoint. One is having A, another B, another C, another D, E. That is equal to the number of vertices initially. Okay, because till now no edge has been added, so there is no chance of cycle. And what is the other point? We have to consider the edges in increasing order of weight. So let us sort our edges in increasing order. So what is the minimum edge? That is AB 1, then DE 2, 1, 2, then BC 3, BC 3, then CD 4, CD 4, then AE 5, AE 5, then AC 7, 5, 7, then AD 10. So these are the edges in sorted order. Sorted order. Now what we will do, we'll consider the edge with minimum cost, and we will add that edge to the tree which is empty initially if it doesn't form a cycle. How do we check that it is forming the cycle or not? We are checking their endpoints are in disjoint set or same set. Okay, so what is my first edge? AB. I considered first edge AB. Now I will check these will form cycle or not. How? These are in different sets or not. A is in different set, B is in different set. So it will be included. So AB has been included. Why it has been included? Because both are in different set. So there is no chance of being a cycle. Okay, and what we will have after these two, these have been added, connected, so their sets will no more be disjoint. They will get a union. Now we are having this set. What is second edge? DE. D is having two costs. So D and E. Let us check. D is here, E is here. Both are in different set. So we can add to the spanning tree. So this is D and this is E. These can be added to the spanning tree with cost 2. Now what to do? Take union of that. D and E. What is the next minimum edge? BC. B is in one set, C is in another set. So again, no chance of cycle. So C, B, 3. Okay, and what will be done? Union. C will also be part of the first set. Next is CD. C is in first set, D is in second set. So we can simply add C and D 4. Next is AE. AE. Now, if we consider AE, after adding this C and D, the union will be taken. We have added this CD, so their union will be A, B, C, D, E. Okay. Now, what we have taken? AE. AE are in both sets, so don't include in minimum spanning tree. Next is AC. AC, both are in same set, don't include. AD in same set, don't include. So this is our spanning tree. 1 plus 3 plus 4, 8 plus 10. So 10 cost. Minimum spanning tree cost is 10. So what we talked about, that is we took separate disjoint sets. We combined the set after adding the edges. It means they have connection, so they may result in some cycle. So whatever edge you include in minimum spanning tree, they should have the endpoints in disjoint set. Okay, so this is KRUSKAL'S algorithm. So in this particular lecture, we talked about greedy approach and we understand the concept of greedy approach with the help of minimum spanning tree problem. It has been successfully applied to minimum spanning tree problem. And for that, we have discussed two algorithms, Prim's and KRUSKAL'S. Thank you. Jai Hind.